So in this video, we're going to look at a couple of examples of resolving indefinite integrals when we have trigonometric integrands. So the first one, we'll start off with a super simple one. We're going to do the antiderivative of the sine of x dx. And we want to recognize there's kind of more than one way of doing this. Maybe I'll walk this through two different ways of thinking about it. So one way is just to look at this and just make a guess. Say, hey, I guess that the antiderivative of the sine of x is the cosine of x plus a constant of integration. And then you check your work. You say, well, if I'm correct, when I take the derivative of my guess, I should get the sine of x back. I should get the original integrand back. But if I take the derivative of this, I realize I have a problem. I get the derivative of cosine is minus the sine of x, plus the derivative of c is 0, because the derivative of a constant function is always 0. And so you get minus the sine of x. So you know that you've made a mistake. So all you would need to do then is tweak your guess and say, hey, when I took the derivative here, I got a negative. So I'm going to have to put a minus sign on it so that I get a double negation when I differentiate, which will give me positive sine x. So I need to adjust my guess to minus cosine of x. So that would be one way to think about it. The other way to think about it might be to do something like this. If I'm taking the antiderivative of the sine of x dx, I could look at this and say, hey, I know that the derivative of the cosine function is almost what I need. It's almost a sine function. It differs by a sign, so it's negative sine x. So what I could do is say, hey, I'm going to take and add a double negation to the integral. I'm going to say the opposite of sine x dx. And this is the same thing as what I had before, because the opposite of a negative will give me positive sine x. So I can just rewrite the integral so that the piece I have here, the integrand, is the derivative of the cosine function. And then I integrate. I say minus. When I integrate, I want an antiderivative of the integrand, the function that's sitting right here. The antiderivative of minus sine x is just the cosine of x, plus I get my constant of integration. So either way, I wind up with the minus sign in front of the cosine to adjust for the fact that the derivative of the cosine generates that negative sign in front of the sine function. So the second example, what you need to remember from example number 2 is that when we're working with trigonometric functions, we frequently need to make sure we can remember our trigonometric identities. So because we might need identities to put things into a form that makes them integrable. And this will, you'll see as we move through the rest of the semester, that these can become very complicated. We shouldn't have any complicated examples in the first homework, though. So I have the integral of sine x over cosine squared of x, and this is dx. And what I want to recognize is that this can be rewritten. I can take that sine x in the numerator and write it over one of the cosines in the denominator. I have cosine squared, so it's cosine x times cosine x. So times, and then I could put 1 over the other cosine function that's in the denominator position. So this is equivalent to the original expression, because sine times 1 is sine, and cosine times cosine is cosine squared. So I've just rewritten it in a different looking but equivalent form. And then I want to recognize that the sine over the cosine is just the tangent function. So that's the tangent of x times, and 1 over the cosine is the secant function. So I get tan x secant x dx. And then what I need to remember from here is that the derivative d dx of the secant function is equal to the secant tangent. So secant x tangent of x. So of course, if I integrate both sides then with respect to x, the integration cancels the differentiation, and I get that the secant of x is an antiderivative of the secant of x, the tangent of x dx. So right here, what I have is a derivative of the secant function. So the antiderivative will just be the secant function plus a constant of integration. And clearly, if we differentiate this, we get back the tangent times the secant.